Hello, I'm Jack. Welcome to my channel, Practical Program with Dr. Su. In this video series, you will learn everything you need to get started with WebGPU Graphics Programming. In this video, I will explain how to visualize complex functions using the domain coloring approach. You can see here on the background is domain coloring for the complex function. This gives the pretty pictures as shown here. Normally, we would need a four-dimensional space to display complex functions, but by using the domain coloring approach to encode the values in the complex plane, we can plot complex functions in two-dimensional space. Domain coloring represents complex functions by assigning a color to each point on the complex plane. Here we will introduce HSV model because this model is closer to how humans perceive the color. The HSV model has three components: hue, saturation, and value. This color model describes the colors in terms of their shader and brightness value. We usually use the HSV color model to associate hue value with the arguments or phase of a complex function, and then convert this HSV model into the RGB model that the fragment shader can use. Here shows the domain coloring for two simple complex functions. The first one is fz equal to z, and another one is fz equal to 1 over z. You can see for fz equal to z, the white circle here indicates the magnitude contours, and the black grid line indicates the real and imaginary parts. You can see that around the zero, the white magnitude contours bunch up, while the black grid line don't, still flat, which means that there is a zero at z equal to 0. While for the function 1 over z, it clearly shows a pole at z equal to 0 because the black, you can see the black grid lines bunch up as the white magnitude circle here get closer and closer to the pole. Here shows these same two functions use different color maps. From this figure, you can still clearly tell the difference between the 0, here's 0, and here's the pole, 1 over z. This pole, you can see the picture is different for the 0 and the pole. In this video, I will show you how to create the domain coloring for various complex functions. Creating domain coloring with animation is a computation-intensive process because we need to redraw the plot pixel by pixel for each frame. So we will perform all the computation in GPU using the fragment shader. Here, we will use the Git tool to clone the source code used in the last video, and then make corresponding changes to the source code to build the project used in this video. Now start Visual Studio Code directly from Windows Start menu. Here, this is Visual Studio Code interface. Now let's start a new terminal window and cd into code folder. cd code. From this folder, we make a new folder called GPU 57. and cd into it. Now we can clone the source code used in the last video with the command git clone WebGPU 56. After this command, leave a space and a period. This will place the source code in the current folder. Run this command. We can check direct. You can see the source code is indeed in the current folder. Now we can open this folder from Visual Studio Code. Open folder, code GPU 57. Here contains the source code used in the last video. WebGPU just released a new version 0.1.15 few days ago, so we will update it to the latest version. Open package.json file. Here we have WebGPU tabs 0.1.14, so we change it to 15 and save it. This will update it to the latest version. Now open a new terminal window and run the command npm install to restore the npm packages used in this example. Okay, finished. Now all the installed packages are stored in the node modules folder. Next, we need to make some changes to the index.html file. From dist folder, open index.html file. Here we need to replace its content with the new code. This file, you can see, contains two drop-down menus. One lets you select a color map. Another one lets you select complex functions. In this example, we define 11 complex functions in the seeder code. In addition, we add the msjax library using a CDN link because we don't want to host this big library. So we will use it to display the mass expression for our complex function. Now we can save this file and close it. Next, we will implement some math functions for complex variables in a separate seeder file. Now add a new seeder file called seedersfunc.wgsl file to the src folder. Add a new file called seederfunc.wgsl. We need to enter some new code to this file. Unlike the functions with real variables, WGSL seeder language does not have built-in function for complex variables. Here we will use vector2 f32 data type to represent complex numbers. That is, we use vector2's x component to represent the real part and the y component for the imaginary part for a complex number. You can see that we first define some commonly used math functions for complex numbers, including C addition, multiplication, division, and square root, complex conjugate, power, inversion, argument of phase, log, sine, cosine, and other functions. Next, we implement a color conversion function called HSV to RGB. This function first calculates HSV components, use magnitude and arguments of the complex function. and then convert them into the RGB color. I should point out here there exist various versions of HSV to RGB color conversion for domain coloring. The version we used here allows you to easily describe behavior of the complex function, such as zeros and poles. Previously, we discussed color map for 3D surface, where we create the color map using TypeScript code. Here, we will implement this color map function in Cedar, which will be used to generate domain coloring for complex functions. You can see here we define a color map function. We use the color map ID to represent different color maps. For example, color map ID equal to 2 represents the HSV color map. Color map ID equal to 3 represents hot color map, particularly for default color map is jet. Here we also implement a color map to RGB conversion function. Inside this function, we first retrieve the color map data with a given color map ID, and then use complex variables z and color map data to calculate the HSV component. You can see with SV component. And finally, we convert this HSV color model into RGB model. Now we can save this file and close it. Next, we need to implement the domain coloring in Cedar. From the src folder, open the cedars.wgsl file, cedars.wgsl file here. Here we need to replace its content with the new code. Here we first create a new function called cfunc that defines 11 complex functions. In this example, we will create a domain coloring for these 11 complex functions. The complex functions can be selected. Use the select ID. You can see we have a select ID to select different complex functions. Here in the Vertex Cedar, we create a 4-point array. Here you can see we have an array with 4 points that will be used to construct a rectangle based on the primitive triangle strip specified in the random pipeline in the TypeScript code. This rectangle is discretized domain for the complex function. In the fragment Cedar, we first pass animation parameter and the window size and select function and select color as uniform variables inside this fs main function. Each point we compute for the complex function corresponding to a fragment in the color buffer. We compute these values by providing the Cedar with the location of the fragment. You can see we define complex variable z in the fragment Cedar using this code. Here, the coordinate in parameter represents the built-in position variable in the fragment Cedar, which provides the location of the fragment in the window coordinates system. We can use these coordinates to generate a color for each fragment. Next, we call the cfunc function with the selected ID here to retrieve the complex function, and then use HSV to RGB or color map to RGB function to create a domain coloring for our complex function. Here, we put the computation intensive code in the fragment Cedar to free up the CPU and take advantage of the speed at which the GPU can perform math operations in parallel. This way, rather than computing the color one pixel at a time using CPU, here we can use the multiple GPU cores to compute up to millions of fragment colors concurrently. Now we completed the implementation for the shader program. We can save this file and close it. Next, we need to make some changes to the main.ts file. From src folder, open main.ts file. Here we need to replace this content with the new code. You can see here does not contain vertex data or vertex buffer because we consider a rectangular region of pixels on the screen, which we create directly in the shader. So you can see here vertex does not contain the vertex buffer here. Next, we create a uniform buffer, which will pass the parameter for animation, window size, function selection, and color map selection. Inside the draw function here, we update the uniform parameter. You can see dt tens. This means we update the uniform parameters every 10 milliseconds. This will produce the animation for our complex function. Please note that our shader module is defined using two separate shader files. You can see here shader. One is shader.wgsl file, one is shader.func.wgsl file. We use this code here, shaders equals shader func and concat shader. So we combine these two files together to form a single shader file here. You can use this approach to combine any number of shader files together. This part of the code here allows you to select different complex functions from the drop-down menu and provides the math expression for the function in the latex format using the mathjax library. This library is specified in our index.html file using a CDN link. Now we finish the modification to the main.ts file. Now save this file. Up to now, we have finished all the programming. Now we can run the following command in the terminal window to bundle our TypeScript code in production mode. npm run prod. Okay, the bundle file is created successfully. Now we can click the Go Live link from the status bar area to open Chrome Canary to view domain coloring for our complex function. So click Go Live link. Here is the domain coloring for function 0 with default color model. You can see the function is fz equal to z minus a divided by z squared plus z plus the a. A is the animation parameter. It can change from 0 to 2. So we just animate this parameter. Right now we can select a different color map. You can see this the jet. You can see clear this is 0, this pose is 2. And it can different color map. Q. This gives very nice pictures. You can also change the function. Default, for example, function 1. This gives square root of this function. This function 1. And function 2 is just the sine AZ. Function 3. This is tan AZ. This function. Function 4. Tan sine AZ. Function 5. Function 6. Function 7. Function 8. Function 9. And function 10. Function 11, that's the Z. This is simple. Zero. So we can use a different color map. For example, we use cool. Then change the function. You can see you get a very nice picture. Function 2. Four. 5. 6. 7. 8. 9. 10. 11. 0. You can also play around with other color maps. Now we have completed this example. In next video, we will discuss how to create a 3D fractal image in the fragment shader. Most examples presented in this video series are based on my recently published book, Practical WebGPU Graphics. From this link, drsu.net.com, you can see the details about this book. I have created a GitHub repository to host the source code used in this video series. From this link, you can download the source code used in this video series. I also created a live demo at this link. This demo shows the live results by running the example projects presented in this video series. I will end this video here. See you next time. Bye.